This is an introduction to using asymptotic notation for program analysis for simple loops. It assumes that you've already watched the video with definitions of the asymptotic notation functions. After talking about what it is we're measuring, I'll give a couple of examples. So, starting with a really simple program, we have like 5 or 6 lines, and each one just takes a fixed amount of time. That doesn't mean that the lines take the same amount of time as each other. The subtraction line is probably quicker than the line with both subtraction and multiplication. But if we're just trying to get the asymptotic runtime of the program, we only need to know that each line individually has some fixed constant amount of time it can take. We then run all the lines and see that the program takes a constant amount of time total. We usually assume that we have fixed sized values. Then we can say that simple arithmetic functions take constant time, but how about square root? That function might actually loop through several iterations of simpler arithmetic, but with fixed size values, we can still say that it takes constant time. For more complex functions, though, you might need to know or calculate their runtime. This simple program takes an array and replaces the maximum value in that array with some new value and returns the old max. Here, we need to be careful of this line. How long it takes to run depends on how large the array is. That might seem really obvious in this context, but when using library functions like indexOf for Java's array list, people sometimes forget. This program takes a constant amount of time plus the amount of time needed to run our findMax index program. So let's step more closely into that function and see how long it takes. It has a loop in it, and if we exclude the loop, the program looks great. It takes some constant amount of time. What constant? Well, we need to allocate some variables, assign some values. I will somewhat arbitrarily call that time 7. It isn't too important in the end because we'll see that it can be brushed into our asymptotic notation. Next, we have the loop. The loop iterates n-1 times, and to get the runtime of the loop, we have to add up the loop's time over all of those iterations. Because I have an upper bound here, to simplify the math, I'll have n iterations, and for each one, we have an increment, a couple of comparisons, maybe an assignment, again, a fixed number of operations. I'll call that 9. So great. Now I have a bound on the runtime for my program, and with just a bit of manipulation, we can see that we can get a linear upper bound on it using our big O notation. Just to show you that the constants I chose here weren't really important, we could do the same calculations with any constants. We can do the same thing for a lower bound. There, even if we ignore any of the program that isn't in the loop and assume the loop takes just 1 unit of time, we can still get a lower bound on the runtime. Here, because both the upper and lower bounds are linear, we've proven that the runtime is theta of n. We could look at more complex single loops, where each repetition through the loop takes a different amount of time, but we can also see an example of that in the outer loop of Bubblesort's nested loops. While Bubblesort's performance is craptastic, its code is very simple and nice for analysis. So there, I'll drop the constant term outside of the loops because I know it isn't going to dominate the runtime. We run through n iterations of the outer loop, and for each of them, there's an inner loop, and we need its runtime. That will be another sum over the iterations of the inner loop. And the time of each inner loop iteration is some constant like 7 again. While the outer loop can have a different runtime each iteration. We sum over all of them, chug through some algebra, and get a runtime of no more than 7/2 n squared, or big O of n squared. Depending on how tight we want to get the analysis, we could have made some simplifications. Instead of working the algebra out perfectly, I could have used more inequalities earlier along the way, simplified the algebra, and ended up still having a runtime of n squared. Now that constant is pretty arbitrary anyway because 7 is pretty arbitrary. On the other hand, if we want to count some key operations, like the comparison or maybe the swap, we could try to calculate that number more precisely. We can get all of those freaking 7s, get rid of them, and say that Bubblesort takes no more than n squared over 2 comparisons. Here I could still simplify the math and say it takes no more than n squared comparisons, But the n squared over 2 term really is more informative, because that somewhat arbitrary 7 is gone, and now the 1/2 means something. In either case, noting that the algorithm's runtime is proportional to the number of comparisons, I still get a big O of n squared upper bound on the runtime. For our lower bound, we use similar math. That simplification from before doesn't work. I can't make the inside loop larger for proving a lower bound. But working the math out, we see the lower order term is now a slight pain, because now we have that we're bigger than n squared over 2 minus something, and for our definition, we want to just be bigger than a constant times n squared. I can't just ignore that smaller term. So I can pick a constant like c equals 1/4 and maybe a positive n naught term and be on my merry way. If I wanted a bigger constant term, I would need a larger n naught. I could actually use any constant less than 1/2, and if I want to use more sophisticated analysis, I could say the number of comparisons is at least 1/2 n squared minus some function that grows no faster than linear in n. That's a lower bound on the number of comparisons by taking an upper bound on that negative function. Combining these results, we have that bubble sort is a big O of n squared and big omega of n squared algorithm, so its runtime grows like theta of n squared. More precisely, it uses n squared over 2 minus big O of n comparisons. What's next? There are really 2 different videos. The first kind of stands alone. It's very quick on different ways that this notation's used. It's light on math and can be watched anytime after the asymptotic definitions video. The other video follows this one more naturally, but starts a whole new series of videos opening the door to more mathematically challenging ways to analyze programs with recursion using recurrence relations. But right now, my friend Toucan Sam tells me he has a bowl of loops that I need to analyze.